Flicker noise, the interface between gate oxide and the silicon substrate in a MOSFET entails an interesting phenomenon. Hence, silicon crystal reaches an end at this interface. Many dangling bond appears, giving rise to extra energy states as charge carriers move at the interface. Some are randomly trapped and later released by such energy states, introducing flicker noise in the drain current. In addition to trapping, several other mechanisms are believed to generate flicker noise. Polysilicon SiO2, dangling bonds, silicon crystal, dangling bonds at the oxide silicon interface, unlike thermal noise. Average power of flicker noise cannot be predicted easily depending on the cleanliness of the oxide silicon interface. Flicker noise may assume considerably different values and such as varies from one CMOS technology to another. The flicker noise is more easily modeled as a voltage source in series with a gate and roughly given by Vn square bar equal to K by C naught X WL dot 1 by F, where K is a process dependent constant on the order of 10 power minus 25 V square F. Note that our notation assumes a bandwidth of 1 Hz. Interestingly, as shown in figure, the noise spectral density is inversely proportional to the frequency. For example, the trap and release phenomenon associated with dangling bonds occurs at low frequencies more often. For this reason, flicker noise is called 1/f noise. Note that equation does not depend on the bias current or the temperature. This is only an approximation. And in reality, the flicker noise equation is somewhat more complex. The inverse of equation on WL suggests that to decrease 1/f noise, the device area must be increased. This is therefore not surprising to see devices having areas of several thousand square microns in low noise applications. It is believed that PMOS devices has a bit less 1/f noise than NMOS transistor because of the former carry the holes in a buried channel that is at some distance from the oxide silicon interface. Nonetheless, the interface between PMOS and NMOS transistors is not consistently observed. Flicker noise spectrum. The above example raises an interesting question: what happens to ion square 1/f dot if the lower end of the band FL is 0 rather than 1 kHz? Equation then contains natural logarithm of 0, yielding an infinite value for the total noise. To overcome the fear of infinite noise, we must make two observations. First, extending FL to 0 means that we are interested in arbitrarily slow noise components. Say noise component at 0.01 Hz varies significantly in roughly 10 seconds and 1 at 10 power minus frequencies in roughly 1 week. Secondly, infinite flicker noise power simply means that if we observe the circuit for a long time, the very slow noise components can randomly assume a very large power level. At such slow rates, noise becomes indistinguishable from the thermal drift or aging of devices. The foregoing observation lead to the following conclusions. First, since the signals encountered in most applications do not contain significant low frequency components, or our observation window need not to be very long. For example, voice signals display negligible energy below 20 Hz, and if a noise component varies at a lower rate, it does not corrupt the voice significantly. Second, the logarithmic dependence of the flicker noise power upon FL allows some margin for error in selecting FL. For example, if the band of interest is so wide that the total indicated thermal noise power is comparable with the flicker noise contribution, then the choice of FL is quite relaxed. In order to quantify the significance of 1/f noise with respect to thermal noise for a given device, we plot spectral densities on the same axis called the 1/f noise corner frequency, and the intersection serves as the measure of what part of the band is mostly corrupted by flicker noise. In the above example, 1/f noise corner Fc of the output current is determined as equation, that is Fc equal to 4 kT 2/3 Gm equal to K by C naught F WL into 1/Fc into Gm square. Figure. Concept of flicker noise corner frequency Fc equal to K by C naught WL Gm 3/8 kT. This result implies that Fc generally depends on device dimensions and bias current. Nonetheless, since for a given L, the dependence is relatively there. 1/f noise on a relatively constant falling in the vicinity of 500 kHz to 1 MHz for these submicron transistors. Thank you.